Good morning, Grace. Sorry, I'm just now getting this video out to you. For one thing, I wanted to make it better, but also I just wasn't able to do it on Tuesday. Anyway, here we go. So this is the answers to the questions you asked about calculus. So the first question: what do limits have to do with derivatives? Well, the answer is everything. Limits, the derivative is a limit. It is a limit process, okay? And so let's remind ourselves, at least we'll use 3 blue, 1 brown's explanation sort of what a derivative is, and we'll show that that has a limit idea and a limit process. So remember, we know how to take the average rate of change, and let's do average rate of change with regards to speed and distance and time. So the average rate of change is going to be, let's say you're at some position, which we'll call P2, position 2, and then minus position 1, so where you started, and we'll divide that by our change in time, so time 2 over time 1. Of course, the average rate of change is your distance you traveled over time, which is just your speed. So the derivative of distance is going to be speed. Sorry, the average rate of change. Okay, but what derivatives measure is it's a very paradoxical idea. Is what is the instantaneous rate of change, right? So what a derivative seeks to be able to do is not just say, okay, how far did we travel from P2 to P1, from time 2 to time 1. It wants to say at time equals 2. How fast are we going? Right, how fast at that exact time? Well, now, in one sense, in no time at all, you're not traveling at all. Okay, and this is one of Zeno's paradoxes. He says, well, how does an arrow move through the sky at all if at each instant the arrow is not moving at all? Right, and so it is this interesting paradox, but we're going to talk later about if there's ways to calculate the mathematics of it while avoiding the paradox. That's what we'll talk about in just a few minutes. And there is a way to do it. But the derivative is a limit. So what it is we want, instead of taking time exactly equal to 2, we're going to take the time approaches 2. So time is going to approach 2. So we'll have the limit as, for example, as t approaches 2 of 2 minus, excuse me. Let me erase that. Of the position at time 2 minus the position at time t. Right, so we want t to get closer and closer to 2 over 2 minus t, right? But if we plug in 2, you can see that we're dividing by 0, right? If t equals 2, that's a problem. But what a limit says is, okay, we're going to get sort of as close as possible to 2 without actually getting there. So for example, 1.9999, and you can put as many 9s as you want to, and that would be okay, right? It's just not okay to plug in 2. So limits have everything to do with derivatives because the derivative is a limit. Now, what do limits have to do with integrals? A very similar answer to this question. We haven't talked a lot about integrals yet, but it's the next big idea in calculus. We're going to start talking about them very soon. And what do limits have to do with integrals? The answer to that question is that, once again, the integral is a limit. So they have everything to do with each other. But what is an integral? Well, let's say we have some rate of change. We can actually use that rate of change function to get back to the distance function. So like, for example, if we know the speed, oops, that's not, didn't mean to put an equal sign. I meant to put an E. If we know the speed equals 8 and the time was 7, then the distance, we can find the distance by multiplying the speed times the time, and the distance would equal 56. Now that's not an integral, but that's sort of the motivation behind the integral, because now, what if speed is equal to 2t squared? The speed is equal to 2t squared. So how would we get the distance now? Well, so what's happening here is that the speed changes over time. The speed, if we look at a graph, this is the speed over time. It's increasing. And so the amount of distance we travel from here to here is not as big as the amount of distance we travel from here to here or from here to here. Okay, and what the integral says to do is actually, if we take the area under this curve, if we take the area under here, and we'll explain why that works. In fact, we'll go over this whenever we come back to class. But if we take the area under here, then that'll give us the distance you traveled from here to here. Okay, and so, but how do you find the area of such a strange shape, right? Where there's just this curve, this parabola, and then these straight lines and all this stuff? Well, the method for finding the area of these strange shapes is actually to use another limit process. So let me erase everything. It's almost finished erasing. Let's say I want to find the area of this shape, what I've drawn here. How could I find this area? Well, there's a way I could estimate the area by making these little rectangles that are sort of evenly spaced. So as you can see, these rectangles here would make a pretty good approximation or a pretty good estimate for this area. All right, as you can see, there is some of this leftover area, like out here, which is so it's a little too big. And then you have like this little bit of area that we didn't find right there. And again, some place out here where it's a little too big. So it's not a perfect approximation, but it's a pretty good approximation for the area. And it's a lot easier to find the area of rectangles than it is to find the area of this weird shape. But what we can actually do is we can get an even better approximation. And the way we can do that is to use smaller rectangles. So if you use little itty bitty rectangles, then we can really get close to the right answer. Whoops. It's harder to draw them though. Right, each one of these rectangles is coming very close to what the function is, and so there's going to be less leftover area. And so this time we were really close. And we can keep making these rectangles smaller and smaller and smaller till eventually these rectangles are basically just straight lines going up and down like this, to where we're actually almost perfectly shading in the area. So, how would we find the area of this? Well, so what we're doing is we're taking the sum of all the rectangles, so the sum of all the rectangles, and it's the sum, but we'll let n be the number of rectangles, and we're finding the area though, so we're finding the base times the height of each rectangle. Well, the height of the rectangle is just whatever the function is equal to at that spot. So the height of the rectangle is just, if this curve is, we'll call y, or f of x, or whatever you want to call it, then this is just y times, and then the width of the rectangles we can call dx, or delta x. That's the width of each rectangle. Okay? And what an integral does is, well, let's take the limit as delta x approaches 0. So that our rectangles are getting skinnier and skinnier, of the sum of each of these areas, which is y times delta x. And so now our sum is getting to be an infinite sum. And so what we're doing is, instead of taking a finite sum of big rectangles, we're taking the infinite sum of really teeny tiny rectangles. And so we call this the integral of, let's say this is 0 and this is 10. We say the integral from 0 to 10 of our function f of x dx. And so that is sort of what an integral is. It's where we're measuring the area under a curve, and it's a limit process. It is also a limit. So both derivatives and integrals are limits. Okay, making calculus rigorous. That was the next question you asked about infinitesimals versus epsilon delta definition. So this actually answers two of your questions. You asked two questions about this. You said, first of all, would dividing a function smaller and smaller eventually give an exact measurement, or only a very close one? And then you asked, how did Cauchy and Weierstrass make calculus rigorous? and you asked, can a derivative measure the instantaneous rate of change at x equals 0 and y equals 0? So yeah, all these questions are good. So you're asking the ultimate paradox, the ultimate question is, what does it even mean to have the instantaneous rate of change? What does it mean infinitely small, right? And so this was the problem. So Newton comes along and he says what? He says that what a derivative is dy over dx. So it's the change in y over change in x. But it is what he calls an infinitesimal He says there's an infinitesimal change in y over an infinitesimal change in x. And the question is, what does this mean? Well, he's saying it's not exactly 0, but it's not a regular number either. It's not a finite number. He says it's an infinitesimal number. It's a number infinitely small. Infinitely small number. The problem is this leads to a huge debate. What do you mean an infinitely small number? How, right? Are we sure that that even exists? What does that mean? Is that something you can actually do? When we ask, is that rigorous, we mean, what is your proof of that, right? Your proof can't be because it seems to work, right? That's not a, we've done some proofs in class. We know it's, you can't just say, well, it seems like it works, therefore I have proof. And that was sort of Newton's evidence. He's like, look, it works. So these other people, such as Cauchy and Weiser-Strauss, come along and they say, well, let's avoid this big paradox of infinitesimal numbers, and let's avoid thinking of it equaling 0 and all this. And instead, what we're going to do is we're going to come up with this idea of the limit definition, the epsilon delta definition, which just says now, instead of it being like an infinitely small, it just sort of becomes as small as you want it to be. For your purposes, for whatever it is you're trying to do. And what's interesting about this new definition of as small as you want is that it avoids having to invent new numbers or address these paradoxes. It sort of avoids the paradoxes and still gives you the right answer without you having to, really question reality as you are coming up with the answer, which is just that a limit, all it's saying now is that for any epsilon you give me, and you say, okay, I want this, the change to be within, only 0.00000001, well then as long as I plug in 0.00000001 into time, then that's going to give you that small of a change in distance. And you can say, I want an even smaller change in distance, and I'll say, okay, I just need an even smaller change in time. And no matter how small of a change in distance you want me to measure, I'll just measure an even smaller time, and it'll work out. Okay, so that's the big difference here, is that we are making calculus rigorous by just saying as small as you want, rather than saying as small as possible. Because the question is how small even is possible, right? So that's the question. So derivatives on graphs, you said, is there a way to show it graphically? right? You said, let me make sure I fully understand the question. It says, here's the way, is there a way to measure such a tiny difference in change on a graph? Or do we think of dy, dx in hypothetical situations? So no, there's not a way. So if we have some curve, all right, and so of course we can measure from, like, let's say from right here to right here. We can measure the average rate of change by drawing a straight line between the 2 points and just saying, okay, that's our secant line, that's our average rate of change from here to here. From here to here. But if I want my instantaneous rate of change right here at this spot, if I just want to know the change right there, then I need to instead have a smaller and smaller approximation, right? And now that's a better one. But instead what we will do is we're going to find the slope of the line tangent to the graph. Oops, I missed. So if you want to think of a derivative graphically, instead of thinking of it as a line that intersects the graph at 2 points, you can think of it as this line over here that only intersects the graph at 1 point. There's only 1 point right there where the line intersects the graph on a derivative. Okay? And so that's sort of the idea of a derivative on a graph. We're finding the slope of this orange line. We're asking, what is the slope of this line? So hopefully that makes sense. And then last, you asked me to find the derivative of the square root x. So this will be a good one to end on. So we have f of x is equal to the square root of x. And we want to find what is f prime of x. Now, one way to do this is to recognize that f of x is equal to x to the 1/2 power. Okay, if you remember from last year, the square root of x is the same thing as x to the 1/2. And so now that we have it written as a power function, we can actually go ahead and use the power rule, and f prime of x will be 1/2 times x to the negative 1/2. And that is totally fine as an answer. But if we wanted to get it back as a root function, so we could say f of x is, so now x to the negative 1/2, that's 1 over the square root of x. And then since this is 1/2, we can rewrite this as 1 over 2 times the square root of x. So that's another way to write f prime. Just rewriting it as like that. So that's the best way, I would say, to find the derivative of the square root of x. Now, there is also a way to do it using limits, but I'll show you that in class. So remind me to show you how to find the derivative of the square root of x in class.